So now that we know what move semantics is, let's come back to our smart pointer template class that we've been developing that's supposed to be able to manage any sort of resource on the heap or the free store. So we looked at how to use move semantics if you have a variable and you want to allow it to be optimized in this way, and that is to say, you want to call a function or do something with that object in such a way that you let the compiler know, hey, you can go ahead and make a shallow copy instead of a deep copy of this object. It's okay, I won't use it anymore. That's when you convert it to an R value reference by calling the move function on it. Okay, the move function will convert it to a temporary R value reference or a temporary variable and assume that you're not going to try to use that object anymore. Okay, so that's how you use move semantics from the point of view of a client or somebody who's trying to work with objects that need to be moved to or moved from. How do you implement move semantics? That is to say, how do you implement that optimization where you make a shallow copy instead of a deep copy? Okay. So what we're going to see is that just like with a copy constructor and a copy assignment operator, the way to get move semantics on your class that you're writing is to implement two more special functions called a move constructor and a move assignment operator. And the move constructor and the move assignment operator, rather than working on regular references to objects of the same type, they're going to work on R value references, those special references we talked about that indicate that that object is temporary and won't be used anymore. If we look here at main, I've just put the same code back that I had earlier. However, I've made a couple of changes. I'm calling process image on manager A, and I'm just making the regular copy that I did last time. But then when I call process image on manager B, I've written standard move. So I'm converting it to an R value reference. So what I would like to happen is I would like this second call to process image be optimized such that it invokes the move constructor rather than the copy constructor. Now, I will say one more thing about the move and copy constructors. The copy constructor is the correct behavior, and it's a perfectly valid fallback, okay? So if your class does not implement a move constructor, and then you try to move that object, it's fine. It'll just end up calling the copy constructor as a fallback. Move constructors and move assignment operators are just an optimization, okay? So you don't have to implement them, all right? So let me go ahead now and implement the move constructor and the move assignment operator. First of all, and in order to demonstrate that the move semantics are not necessary, okay, they're optional, you can opt into them. Let me just go ahead and run this code. I'm going to call standard move on this object, but we have not implemented a move constructor or a move assignment operator. And because we haven't done that, we're just going to end up falling back to the copy constructor. No big deal. Okay, so if we compile and run this code, we create two images, A and B. Okay, the smart pointers are created and those image objects exist at different memory locations. These are slightly different memory addresses. Okay, now when we call process image the first time, we're passing the smart pointer by value and we're making a copy and we are making a deep copy. Notice copying image A from image A, right? So we're making a completely new image at a completely new memory address. That is a deep copy, okay? And this process image function runs to completion and then it exits, and so I destruct the image that I had just made. Okay, so this is the image I just copy constructed and now it's being destroyed. All right. And then manager B is passed to process image using move semantics. However, move semantics are not implemented for my smart pointer yet, so the same exact thing happens again, but this time for the image from manager B. Notice this is the image from manager B. Okay, this is the image that is then copied, deep copied, I might add, and then destroyed. Okay. And then once I get back to the main function, manager B and manager A go out of scope. So those original images that they had, that they have as data members are then destroyed. Right. So I'm trying to use move semantics to get that optimization, but nothing's happening. It's just falling back to copy construction and copy assignment. All right. So let me go ahead now and turn on move semantics by implementing the move constructor. All right. So the move constructor is very similar to the copy constructor. Let me go ahead and let me just go ahead, in fact, and copy this line of code. We're going to see how similar it is. So the thing is, we're not using a regular reference anymore. We're using an R value reference. So the move constructor takes an R value reference. And we are not going to be able to take a const reference to this object because by definition, a temporary value, in order to get move semantics, we're going to have to change or reset the state of that object. So it doesn't make sense to have a const object because then we wouldn't be able to reset the state. So a move constructor takes a non-const R value reference indicated by the double ampersand sign, a non-const R value reference to another object of the same type. Okay. And then what it's supposed to do is not perform a deep copy. So this is wrong. This is wrong right here. It's supposed to not perform a deep copy. Rather, it's supposed to perform a shallow copy and reset the state of the other object. So I know in a constructor you're supposed to implement things in the implementation list. I'm about to do that, but first I want to make it very clear what I'm trying to do. Okay, so I'm creating a new object. Okay, so my resource is going to, and instead of doing, creating a new image on, or a new object of type T on the heap, I'm just going to go ahead and copy the memory address from the other object's resource. Okay, it's totally fine to do that. This led to segmentation faults in the past, but because I have move semantics, I know that, hey, I can take this memory address so long as I reset the other smart pointer's address to be null pointer. Okay. So notice what I'm doing here. I am doing the shallow copy, but I'm also resetting the state of the other smart pointer. Okay. It would be an error. Oops, it would be an error to forget to do this. This would again lead to the segmentation fault we saw earlier. But it's perfectly fine to do this. It's perfectly fine to reset the state of the object we are copying from. Now, if you think about it, a copy means the two objects are supposed to be exactly the same. So this is not a regular copy because after this function, after this constructor runs, the objects are not the same. The object we copied into that we're copy constructing is a copy of the original object called other, but other has been changed. Its state has been reset. Okay. This gives us that optimization from move semantics. And this copy or this move constructor will only ever be called when we explicitly ask for it by saying standard move and then passing the object to the constructor. Okay, so hopefully that makes sense. You have to explicitly request move semantics, and then the optimization will be taken. And because notice how we're resetting the resource to null pointer, it would be completely nonsensical to try to use manager B after this line of code, because the image that it refers to is just a null pointer, right? So again, it's kind of like a contract between you and the compiler where you're saying, hey, you can go ahead and optimize the copy of manager B. I'm not going to use it anymore. Okay, so this is almost what we're looking for. However, being the fact that this is a copy constructor, we should actually be doing all of this inside of the member initializer list. Okay, so we need to do something right here where we essentially do these 2 lines of code inside of this 1 line of code. Okay, and it can be done. There's a special helper function called exchange, where you provide the value of the thing you are let me just go ahead and write it. So other.resource and null pointer. What this basically does is it sets the value of other.resource to null pointer, but then returns the original value of other.resource. It's kind of, yeah, it's just a helper function that on this line of code, it does what these 2 lines of code. So to best understand what's going on, look at these 2 lines of code. Okay, but when you actually implement this thing, because it's a copy constructor, you want this to all happen in the initializer list. So this is what you actually write. Okay. Yeah, so you can just try to remember that, or actually don't memorize this. You can always just look up what this is supposed to. Actually, I'm going to show you that you almost never actually need to do all of this work anyways. Okay, so the one other thing now that we should do, well, hold on. Before I do the copy assignment operator, let's go back here and let's rerun this code. And we should see that we're getting the optimization already. So let's run this code, and I want you to compare it to what we had previously. So the first time we ran the code, we made 2 different copies, right? Notice the second time we run the code, we're only making 1 copy, okay? And that's coming from when we call process image on manager A and do that whole copy construction, okay? So we call process image, so everything up to here is the same. Okay, so the first 1, 2, 3, 4 lines of code or of printout are the same. Okay, these 2 lines of code and the last 2 lines of code are the same. So these 2 lines of code, or not lines of code, lines that are printed out, don't happen now that we've implemented move construction. Okay, because when we call process image for the second time, rather than making a deep copy of the underlying image and then having to destroy that image when we exit the function, when we call the function, we just go ahead and steal the underlying data, pass it to the copy of the manager that's inside of the function. There's no deep copy, it's just a move now. And that's it. And then when the function's done, it actually destroys image B. Notice, yeah, image B is destroyed. Notice it actually destroys image B. This destruction of image B is actually happening when process image exits. There's nothing to destruct when we exit main because B has been reset to null pointer once we get to main. So there's nothing deleted. So the one other thing that we should do is we should see what happens with move assignment. So let me go ahead and let me just simplify everything here. So we're just going to create 2 managers, manager A, manager B, 2 different images. And instead of just assigning manager A equals manager B, we're going to move assign manager B into manager A. Okay. Of course, if we were to just run this code, because we haven't implemented the move assignment operator, we're just going to get a regular assignment. Okay, so if we run this code, again, we're creating 2 images. And then when we do this copy, so remember, we're not getting move semantics yet because we haven't implemented the operator. So it destroys the initial image from A, and then it makes a copy of the image from B. Okay, so these two things happen on this assignment operator, and then when the main function exits, both of those images are destroyed. Okay, so let's go ahead and optimize this now by implementing the move assignment operator. So I will again just copy the copy assignment operator, and exactly for the same reason, the copy constructor takes a non-const R value reference. The move assignment operator will also take a non-const R value reference. Okay, so that's the first thing to keep in mind. Much of the implementation is still the same. So everything on the outside, so the if guard and returning star, this is still the exact same. It's just the behavior of the assignment operator. But what we do on the inside is going to be slightly different. So initially what we did was we deleted the resource and then made a new copy of the underlying data from the other smart pointers resource and stored that pointer as our own resource. Okay, we still need to delete the resource. Okay, but now we don't need to make a new object on the heap. We can just, again, grab the object or grab the pointer from the other object but we can only do this if we also remember to reset the other object's pointer to be a null pointer. Okay, so we can just and we shouldn't dereference either. So we can just make a copy of the memory address and store it in our pointer, our underlying data member, which is a pointer, right? And this is only okay to do if we also reset the other resources, the other smart pointer's resource to be null pointer. And, just like we did with the copy constructor, we can also use this exchange function. That works fine as well. Just a little bit more concise. Okay. So now that I've implemented the move assignment operator, let me rebuild the code one more time and run it one more time. And you will see that we're getting that optimization. We're getting that shallow copy because we've let the compiler know we don't need to use manager B anymore. It can be temporary. Run main, and notice that again, these two lines of code were completely, or not lines of code, these two lines of printout were completely eliminated because we didn't destroy and then copy. In fact, it was actually these two lines that are eliminated. So we do destroy the image when we first we do delete the resource, but then rather than copying and then deleting the other resource, we just steal the underlying data, right? We steal the underlying data, and then when A and B go out of scope, B has nothing to delete, and A deletes the image that it had stolen from B. Okay, so that is move semantics for you. So I know that this is pretty complicated. It can be quite overwhelming. But you need to understand, like, you don't have to understand or you don't have to memorize how to implement all of these things. It is quite a lot to remember, but you need to understand what's going on. You need to understand that move semantics is an optimization, which you can opt into for the classes you're defining. If there's some sort of resource that's large and you don't want to make copies of it all the time, you can opt into it by providing a move constructor and a move assignment operator. And if you do opt into it, the clients of your class, the users of your class, will be able to request that optimization so long as they let the compiler know that they're not going to use the object they're moving from or copying from anymore after that line of code. Okay. And there are several scenarios where you might want to do that. Okay, so it is something that is extremely useful and valid to do. So why do we say the rule of 5? So we talked about the rule of 3, how if you implement the destructor or copy constructor or copy assignment operator, you probably should implement all 3 of them. So when it comes to move semantics, there's actually another rule called the rule of 5. And the thing about the rule of 5 is just like an extension of the rule of 3. Okay, the rule of 5 says that if you are using the rule of 3 and you want to optimize, so the rule of 3 gives you correct behavior. But if you also, in addition to correct behavior, want to allow for the optimization of move semantics, then you have to implement all 5 of the functions. Okay. So again, if you implement any one of those 3 functions, you probably have to implement all 3 to get correct behavior. And if you also want your code to be optimally fast, you have to implement all 5, including adding the move constructor and move assignment operator to what you're implementing. So that's the rule of 5.